Hello students, welcome once again to another session of Econometric Methods course. Today we are going to see an important and interesting topic in the econometric analysis. We are going to see the relationship between regression analysis and econometrics. So let us see what this regression analysis is about. Regression analysis is a branch of statistical theory that is widely used in almost all scientific disciplines. Regression analysis is a statistical technique that attempts to explain movements in one variable, the dependent variable, as a function of movements in a set of other variables, we call it independent variables, through a single equation. Regression analysis is concerned with describing and evaluating the relationship between a variable, we may call it dependent variable and denoted by y, and an independent variable denoted by x. If there are more independent variable, we may use x's with subscripts, that is x1, x2, x3, etc. In literature, we use different names for dependent and independent variables. Let us look at the table. Effect variable and causal variable, predictant and predictors, regressand and regressors, explained variable, explanatory variables, target variable, control variable, are all the different names given for dependent and independent variables. The primary instruments used in any regression analysis is the regression equation. The dependent variable is described as a function of independent variables, that is y equal to the function of x1, x2, x3, etc. Regression equation is a mixture of variables and coefficients, symbolically described as Greek alphabets, say beta 0, beta 1, beta 2, etc. in the following order. Look at this equation: y equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, etc. up to beta n xn. The coefficients of the equations are estimated using the data on relevant variables with appropriate estimation technique. The equations would represent the nature, magnitude and causality of relationship. Let us see some of the features of regression model. 1. Regression equation is a mathematical expression of relationship between related phenomena, cause and effects. More specifically, regression equation is an algebraic expression. 2. Regression equation would describe the relationship with a single regression function or with more related regression functions. 3. Parameters we here will denote as constants and coefficients characterize the regression equations. Parameters measure important behavioral benchmarks of the system, could be estimated from the observations as stated earlier. 4. Estimated values of parameters could be subjected to inferential tests. Regression is adaptable to confirmatory framework because of this feature. 5. Regression analysis is also a versatile modeling technique, that is, it can be used in diachronic and synchronic adaptations and make the technique very robust. 6. Regression helps to control the effect of extraneous forces with simple addition of variables in the left hand side. 7. Regression analysis is a statistical device with the help of which we are in a position to estimate the unknown values of one variable from known values of other variables. In other words, regression analysis provides estimates of values of the dependent variable from the values of the independent variables. Algebraic equation of regression allows, because of this feature, for prediction and forecasting. 8. Change of parametric values would help simulate various policy scenarios. 9. Regression is flexible enough to include all types of variables, including qualitative variables. 10. Many core concepts of regression analysis establish a good foundation for understanding other multivariate techniques like factor analysis, cluster analysis, structural equations models. It can be used to model curvilinear data by transforming the raw data, typically with logarithmic or power transformation. These transformations can linearize the data so that simple linear regression can be used to model the data. 12. Regression analysis enables the one to obtain a measure of error involved in the using of regression function as a basis for estimation. These features may be helpful to carry out the scientific investigations with the following objectives. 1. We may use it to examine whether any of the x's have a significant effect on y. 2. Forecast the value of y for a given set of x's. 3. Analyze the effect of y on x's. Now, let us see how econometric analysis and regression equations are related. In practice, there are prominent quantitative approaches in economics, that is, quantitative economic models approach, economic statistics approach, mathematical economics approach. Econometrics unifies all the quantitative traditions in economic analysis. Economic theory, mathematics and statistics are used to estimate numerical values for economic relationship and verify economic theories. Regression analysis is amenable for the use of all the quantitative traditions, and so is a magical tool in the hands of econometricians. Much of economics and business is concerned with cause and effect proposition. For instance, quantity demanded, that is a dependent variable, depend on the price of a commodity, the prices of related commodities and the income of the consumer, all are independent variables. If the price of a good increases by 1 unit, then quantity demanded, that is independent variable, decreases by a certain amount. All this can be quantified. Econometricians use regression analysis to make quantitative estimates of economic relationships that were theoretical in nature. The direction and strength of the relationships anticipated in the theory are derived from the coefficients of the regressions estimated using sample data. However, there is a significant difference between the regression analysis and econometric analysis. The relationship equation is complete and exact in the regression analysis. The regression analysis was mainly developed for the physical and natural science investigations. Exact determination of relationship in the controlled experiment of those sciences is possible. Laboratories based experiments manage to control the influence of variables not included in the model, and so regression techniques best suited to the experiments based studies. Complete determination of economic relationships is not possible. Exact functional relationships are inadequate descriptions of economic behavior. The exploratory analysis is popular in the natural or physical science investigations. The regression is used in the atheoretic exploratory context in those sciences. In econometrics, regression analysis is recasted for the purpose of economics. The econometric analysis is essentially confirmatory in nature. Economic research is non-experimental research, where extraneous variables and other variables are not controllable. Traditional cause and effect studies cannot be done with randomized assignments in economics. The regression has to be modified to accommodate the research designs with counterfactuals in economics. Therefore, in economics, it is not possible to conduct studies based on controlled experiments, and also the variables not included in the study may tend to influence the relationship. It would be impossible to predict y only with the help of x. There will be inherently unexplained variations in the regression analysis. Econometricians admit the existence of such unobserved variations in y. The unobserved variations explicitly included as a stochastic or random error term or disturbance term in the regression equation. The error term comes from the philosophy that all the variations in y cannot be explained by the included x's alone. These error terms are usually denoted by the symbol u. Although other symbols like v and epsilon are used, u is the most popular symbol. Econometric analysis effectively treats all the factors affecting y other than x as being unobserved, and the symbol u stands for the unobserved. U represents factors other than x that affect y. This unpredictability would exist even if large number of explanatory variables were included in the model. Therefore, it may be safely concluded in the regression framework that y is essentially stochastic or non-deterministic in nature. Therefore, the econometric model is described as y equal to beta 0 plus beta 1 x1 plus beta 2 x2 etc. beta k xk plus u, where y is the dependent variable, x's are independent variables, beta 0 is intercept term, other beta i's are partial regression coefficients, and u is a stochastic term. Hence, in a single independent variable case, the expected y given x or the conditional average of y equal to alpha plus beta x is more realistic than y equal to alpha plus beta x as in the regression analysis. Alternatively, it may also be concluded that if at all any relationship exists between the dependent variable and the independent variable, the relationship is on an average relationship. Extending this logic further, there be some error component which is essentially random or stochastic apart from this component that could cause unpredictability of y. That is, y is equal to the expectation or conditional expectation of y given x plus stochastic error. Substituting this in the above, we would get y is equal to alpha plus beta x plus u, where u is a stochastic or random error. This single regression equation may also be called the model, as it is conceived as an abstraction of reality. The introduction of u into the traditional regression model is called the econometric model. Let us see the reason for the inclusion of the disturbance term u, or otherwise the sources of disturbance in the regression model. A stochastic error term is introduced to explain all the variations in y that cannot be explained by the included x's. The following possibilities explain the existence of a difference between the observed values of y and the values expected from the deterministic component of the equation, that is the conditional expectation of y given x, that is y minus conditional expectation of y given x, or random error term u. So, the u is included because of the misspecification possibilities, misspecification of model or omission of explanatory variables is one important cause for the inclusion of u. U can be assumed as a substitution for all omitted or unobservable variables. U could be taken as a proxy for all the omitted variables in the model, and when no information is possible for an important independent variable. Consumption in a particular year may have less than it would have been because of uncertainty over the future course of economy. Since this uncertainty is hard to measure, there might be no variable measuring consumer uncertainty in the equation. In such a case, the impact of the omitted variables, that is consumer uncertainty, would likely to end up in the stochastic error term. Second most important reason for the inclusion of u is the parsimonious model. U helps to keep the model very simple. When the joint influence of those omitted variables are very small, this u will come as a handy variable. 3. Random human behavior can also be explained with u. U helps to handle the intrinsic randomness of the behavior of human beings. For instance, the consumption function attempts to portray the behavior of people, and there is always an element of unpredictability in human behavior. At any given time, some random event might increase or decrease aggregate consumption in a way that might never be repeated and could not be anticipated. There are other possibilities for the inclusion of u. 4. Functional misspecification. U helps to address the ambiguity in specifying functional relationship between the dependent and independent variables. When there is a possibility of other mathematical forms of relationships, A, the underlying consumption function may be non-linear, but a linear consumption function might have been estimated. In this case, there is an error. So, this error is caused by using a linear functional form to non-linear relationship. Look at this diagram, you can see how this error is generated. Another possibility is, let us say 5, measurement error. U helps to manage the problem of measurement error, which cannot be avoided in the variables included in the model in the economics context. The measurement error would arise in practice when the theoretical variables proxied by the data variable. The observed amount of consumption may have been different from the actual level of consumption in a particular year due to an error such as sampling error in the measurement of consumption of national income accounts. 6. Aggregation of variables. In many cases, relationship is an attempt to summarize in aggregate number of microeconomic relationships. For example, the aggregate consumption function is an attempt to summarize a set of individual expenditure decisions. Since the individual relationships are likely to have different parameters, any attempt to relate aggregate expenditure to aggregate income can only be an approximation. The discrepancy is attributed to the disturbance term. For the ith individual, the slope or beta may be beta I. For the ith individual, the slope may be different jth individual, that is bj. Naturally, bi not equal to bj and not equal to beta. These possibilities explain the existence of a difference between the observed y and the values expected from the deterministic component of the equation, that is conditional expectation of y, and also the rationale for the inclusion of u in the regression model. Let us sum up what we have studied so far. In this session, we have seen the importance of regression models, features of regression models, and the difference between the regression model and the econometric model that arise from the inadequacy of regression model to address the problems of research in economics, and so econometrics is born. In the econometric models, with the traditional regression model, an important stochastic error variable u is added. We will see the implications of it in the sections in the next session and the sessions that follow. Thank you so much.